In video 99 of Tensor Calculus, we'll follow up our previous video by deriving a tensor calculus expression that is roughly equivalent to the Gauss-Bonnet theorem. Suppose we have a small parallelogram here defined by two vectors, du alpha and dv beta in this direction. Well, let's see what happens when we parallel transport a vector t around this parallelogram in a counterclockwise direction. We're going to parallel transport from point P0 to P1, then to P2, P3, and back to P0 again. Okay, well, to do that, we'll start with one of the forms of our parallel transport. It's simply this one. The change of our vector is equal to this bilinear form. And note my notation here. What we're saying is that this is the change of the vector as we move from point P0 over to P1. So as we parallel transport along this line, this is the change of our vector t. It's simply one of the definitions of our parallel transport. All right, well, let's move on and find the change of the vector as we move from point P1 to P2. So using our notation, we'd say that the change of vector t lambda from point P1 to 2 is going to be exactly the same form as this. It's a parallel transport, but I will use different indexes this time. We'll use the same free index of lambda, but I'm going to use beta and sigma here. Okay, but the value of our Christoffel symbol is different at point P1 than it is at point P0. Here, these are the values as they're evaluated at point P0, but I have to use values for this expression as they exist at point P1. So we'll represent it this way. We'll say that this is the Christoffel symbol evaluated at point P1, whatever that is. We'll delve into it in just a minute. And also the vector t omega, well, I'm using sigma here as my dummy index, so t sigma, again we have to designate that it's the value of that vector evaluated at point P1. And the displacement is not du alpha, it's dv beta as we move in this direction. So this is the form for the parallel transport along this segment. Okay, well, what about these two guys? How do we figure out what those look like? Well, we'll start with gamma lambda beta sigma evaluated at P1. Here we're just going to expand this out using the Taylor series. So the Taylor series says, first of all, we start with the function at P0, so that's just gamma lambda beta sigma, and we add a term that involves the partial derivative of our function with respect to our coordinate value, and I'll use the index rho this time, so it's with respect to s rho, times the displacement, which is du rho. Now, of course, the Taylor series would be an infinite series here, but we can ignore all the other terms, and the reason we can is that this is an infinitesimal value. The next term would have this factor squared in it, and then cubed, and then to the fourth power, and so on. Each successive term is one higher order than the one before it. And because this is an infinitesimal value, as we find the limit of this, these other higher order terms will go to 0, so we can simply ignore them. We only need the first two terms of the Taylor series to get the right expression for this guy. Okay, well, what about the vector itself? T sigma evaluated at point P1 is going to be equal to the value of that vector at point P0 plus whatever infinitesimal change occurred as we transported from here to here. Well, we've got that value right here. This dt lambda is the change of the vector as we move from here to here, so we simply have to add this particular term to this one to get the value of the vector at P1. Of course, I'm using a different free index here, So it's going to be minus gamma sigma alpha omega times our vector t omega and du alpha. So these then are the expressions, this one and this one, that we simply need to substitute back in here and here. Next, we'll use the distributive property and expand everything out to individual terms. For this first term, we simply took the negative of this factor times this one times this. For the second term, right here, it's the negative of this factor times this one times this, and so on, to expand every term out in a similar fashion to get individual terms. Okay, now notice here that we have a first order term here. We have two second order terms and one third order term. Well, consistently with the discussion we had up here, we don't need to retain all these terms. What we're going to do is simply to ignore the third order term. Now, it's the same reasoning as before, because this third order term will be insignificant and will go to 0 as it's compared to terms of lower order. But we are going to retain everything up to the second order, and you'll see why in a few minutes. Okay, well, I will rewrite this expression now after renaming a couple of indexes. I'm going to rename sigma here to omega. I'll rename sigma here to omega, and I'll rename rho to alpha. Now the reason for doing this renaming is that it gives us the same factors here that we have in this term. So you'll see how that plays out in just a minute. All right, well, let me clean this up a little bit. First of all, we'll get rid of the intermediate work here, and then we will move this up, consolidate a little bit right up into this position right here. So what we have right here is an expression that tells us how the vector changes as it's transported from point P0 to P1. And this expression tells us how the vector changes as it's transported from P1 to P2. So if we're going to have an expression that tells us how it changes from P0 all the way to P2 by way of P1, then we simply need to add these two expressions together. All right, well, now we're halfway around the diagram from P0 to P2, so we've got to complete the transport process all the way around here. So we have to find an expression that gives us the transport from P2 to P3 and then P3 to P0. But the interesting thing is that this transport process is the opposite of transporting in this direction. In other words, if we found an expression for transporting from P0 to P3 to P2 and subtracted that result from this one, then we would accomplish the same thing as going all the way around the curve. So what we need now is an expression for how the vector will change when transported from P0 to P3 to P2. Well, the interesting thing is that the steps that we do here are exactly the same as the steps here if we replace u with v and rename alpha to beta and beta to alpha. It's exactly the same calculation going this way as this way, except interchanging both the variables and the indexes. So what we're saying is that we can find the change of the vector dt lambda from P0 to P3, then to P2, simply by taking this expression and replacing u with v, v with u, and swapping the values of alpha and beta. Now all that's left is to add this expression and subtract this expression. And when we do, notice what happens. This term cancels this one, and this term cancels this one. Now, at this point, you can see why we had to hold on to the second order terms, because all of the first order terms cancel each other out, and we're left with only second order terms. All right, so also notice here that throughout this expression, all of the remaining terms have the same three factors right here. So as we add these and subtract these, we can group all of the factors together and then take the common factors outside. So it's going to look like this. All right, well, this term is right over here. There's a sign change because remember we're subtracting this second expression. And then this term is right here. And we have this term right down here. And this one right here, again with a sign change because we're subtracting. All right, well, this expression right here is the one we derived back in video number 82 for the Riemann-Christoffel tensor. So that means we can write our final result in this form. The change in the vector dt lambda is equal to this expression, which is really the Riemann-Christoffel tensor, or lambda omega alpha beta, contracted first of all with our vector t omega, and then with our transporting vectors du alpha and dv beta. What this expression tells us in tensor calculus format is essentially the same thing we learned from the Gauss-Bonnet theorem, and that is when we transport a vector around a closed loop on the surface, the incremental change of that vector is directly related to the product of the curvature of the surface and the area enclosed by the closed loop. Notice that when the Riemann tensor is 0, dt lambda is also 0. Thus the vector remains constant if and only if the surface is flat. The idea of transporting vectors from point to point for comparison is only possible for the special case where the manifold is flat. All right, with that, let's finish up with a quick review. What we did in this video was to derive this expression. It is a tensor equation that is roughly equivalent to the Gauss-Bonnet theorem that we explored in the last video. It tells us that a vector that is transported around a small area represented by this product right here, this is the area of a small parallelogram. When we parallel transport a vector around that small parallelogram, then the vector will change depending on the curvature of the surface. And when the curvature of the surface is 0, of course, there's no change. And that just tells us what we've known all along, that a vector that's parallel transported in a closed loop on a flat surface will not change. But if it's transported around a curved surface, it will change. And this is the expression in tensor calculus that quantifies that effect. It tells us how much the vector changes as we transport it around this small incremental area.